Hello, this is mathjazz from Almost Cool. This is the third video in our series of videos on the box modeling problem. In videos 1 and 2, we set up a function to describe the volume of a particular box, and we took the derivative of that function. In this video, we will use the derivative to figure out what the maximum volume of this box is. Here's the question. Suppose that you have a rectangular piece of cardboard of width 24 and length 16, and you cut squares of side length x out of each corner so that the resulting piece of cardboard can be folded into a box. E. What is the maximum volume for a box made this way? I have a diagram of the flat piece of cardboard on the left with the corners cut out, and a diagram on the right which is the box when all of the flaps have been folded up and glued together. So, if you haven't done parts A through D, you should watch the other two videos in this playlist first, so that when you get to this video, you have the other parts of the problem finished already. Please pause the video to solve part E. When you unpause the video, we'll see the solution to part E. Part E. From part C, we know that the derivative of the volume function is v prime of x equals 12x squared minus 160x plus 384. To find the maximum, we set the derivative equal to 0. 0 equals 12x squared minus 160x plus 384. Using the quadratic formula, we find that x is equal to 160 plus or minus the square root of 160 minus 4 times 12 times 384 divided by 216, which simplifies to x equals 20 plus or minus 4 times the square root of 7 divided by 3. Since 20 plus 4 times the square root of 7 over 3 is greater than 20 plus 4 times 2 over 3, because 7 is bigger than 4, so the square root of 7 is bigger than the square root of 4, and the square root of 4 is 2. So we know that 20 plus 4 times the square root of 7 over 3 is bigger than 20 plus 4 times 2 over 3, which is bigger than 28 over 3, which is bigger than 9, and the domain of the volume function was from 0 to 8. We know that this root lies outside the domain of the function, so it is an invalid critical point for this problem. So x equals 20 minus 4 times the square root of 7 over 3 is the only critical point in the interval. Further, the endpoints of the domain give a volume of 0, so if we extend the domain to include 0 and 8, we get boxes of volume 0 because they are, respectively, a height of 0, so the volume is 0, and we have a width of 0, so the volume is 0. So, on the closed domain from 0 to 8, there is one critical point at x equals 20 minus 4 times the square root of 7 over 3. And so when we check the endpoint values for our domain, and we check the critical point, we find 0, 0, and some positive number at x equals 20 minus 4 times the square root of 7 over 3. So the positive number must be the maximum value of the volume equation. And 0, of course, is the minimum. Plugging our critical point into the volume equation will give us the volume of the box at its maximum. So v of 20 minus 4 times the square root of 7 over 3 is equal to this polynomial with 20 minus 4 times the square root of 7 over 3 plugged into it. And if we evaluate that, we get a number that is just a little bit less than 541. I think it was 540.8 something when I did it. And that is the maximum volume of the box. Thank you for watching this video. Contact information is on the screen, also in the video description below. I hope that you're enjoying learning calculus. I hope that you're having a great day, and I hope that you found this problem enlightening. So, again, have a great day, and goodbye.